One of the purposes of statistics is to summarize data. So we may have a set of data, it could be very large, and it's hard to just look at a bunch of values and try to tell what's going on, to look for obvious patterns. So we probably learned, well, we've certainly learned the idea of a mean. The mean gives us some sense of center. And we'll focus on interpreting the mean here. Sometimes this is called the expected value, especially just as a general definition, the mean is the expected value. And the mean by itself is not a good indicator of just summarizing the data, because it tells us the central value, but it doesn't tell us how spread out the data is. The spread, there are lots of different ways we could measure spread. There's lots of different ways we can measure center. But we're going to focus just on mean and standard deviation as a way to measure center and spread. So as an example, to see why this is important to have spread in addition to center, we have two cities here and they have the same average home price based on a small sample of data. Now it's a very small sample of data. I made these up, but just so that we have the illustrative purpose. Do both cities have equally affordable housing? Well, first of all, I see that the average, 300 plus 350 plus 400 divided by 3, is going to come out to 350. Similarly, 340 plus 350 plus 360 divided by 3 comes out to 350. So same average, but we can see here that in City 1 has more extreme house prices. They have a much lower house price as well as a considerably higher house price. Whereas in City 2, those houses seem less spread out. So if I created just a little number line here for each of these two cities. Let's say I have a number line and then a number line for City 2 as well. And I just plotted this data on here, then we would see that both have an average value of 350. But then City 2 has these house prices over here at 300 and 400, whereas City 1 has house prices of 340 and 360. So we can see that there's more spread in the house prices in City 1, and there's less spread in City 2. So based on this data, we might say it's probably a little bit more affordable to live in City 1. I mean, as far as purchasing a house goes, because you can find lower priced homes than in City 2. They all tend to be kind of clustered around 350. Now, one of the questions is, how do we measure? How do we measure this? Right? Here we can see that one is less spread out than the other, but we need some sort of metric, and that's going to be the standard deviation, which we'll soon see. But before we get into that, we have to distinguish in statistics between what we call a sample and what we call a population. So in the context of the house prices, we think of the population as this bigger circle, and this could be thought of as all homes in, say, City 1. Now, we probably, if we're collecting data, we don't have the time or the resources to sample every single home. So usually what we do is we hopefully at random, as randomly as possible, select a series of homes, and we form a smaller pool, which we call the sample. And that's going to be a random selection of, we'll just say, n homes. Okay, so we form this sample. It's a way of getting an idea of what the house prices look like without having to sample all of them. Now, the reason we want this to be random is because if I just grab the first 3 houses that I see on a website, those could be being promoted by an advertiser, and so we don't want to necessarily create a biased sample. We want a representative sample. And so by selecting things randomly, we ensure that we give every house an equal opportunity of being selected and therefore represented. So our sample is hopefully, should fairly represent the population. Okay, so that's why we go with random. Now, there are, depending on, in some cases, you may actually be dealing with an entire population. For example, let's say I choose one of the classes that I teach and I sample everybody's score on a quiz from that class. Well, then I have the population of all students in my class. But let's just say that I think about all of the students at the college and I sample just my class. Well, now my class is a sample, and the population is the set of all students at the college. So it really depends on context. Who are you trying to make conclusions about? So in this example, if we want to make a conclusion about all homes in City 1, then our sample should be a random sample from all of the homes in City 1. If the population that I'm trying to describe is my classroom, then my population is the set of all students in my classroom. However, if my population of interest, if I'm trying to describe all students at the college, and I just select 30 of those students, well, now my sample is a smaller subset of all students at the college. Now, so that means that if in the situations where we do collect data on the entire population, we can compute the mean. And similarly, if all I do is collect a sample from that population, I can, well, still compute a mean. And you can see that it's just the sum of the values divided by the number of values. So I'm not going to really be very precise here in statistics speak, meaning that we really should use capital N for the population and lowercase n for the sample, but n is just the number of values. And we remember that this symbol just means sum up or add up all of the x's. So our purpose is not to get extremely precise here, but just to give an overview. So we have the population mean, and then over here, based on the sample, we can compute a sample mean. So same idea, add up the values, divide by the number of values. Now, we can also get this metric that we're going to talk about, this measurement of spread, and we could, of course, if we have a population at hand, then we could calculate the spread for our entire population. And the symbol we use for that is this Greek symbol, sigma. Okay, so I'll just point these out so you know what to call these. This is called mu, the Greek m, and this is called sigma. So we often use Greek letters to denote things about the population, and lowercase letters to denote those same quantities about our sample. Okay, we'll talk more about the calculation here, but then instead of using sigma, which is just an S in Greek S, we use just a lowercase s to denote that sample standard deviation. Now there is a little bit of a difference in the computation. Notice that we're going to add up some stuff, and what we're going to add up is the square of the difference between each value and the mean. Okay, same thing here, x minus x bar and x minus mu, same idea, it's just the value minus the mean, value minus the mean. Square them, add them all up. The only difference is that in a population, we divide by the number of values. For a sample standard deviation, we divide by the number of values minus 1. Why do we do that? Well, all I'm going to say is this. The answer is it's kind of a little bit more complicated, but the idea here is, in short, it makes the sample standard deviation what we call in statistics an unbiased estimator for the true population standard deviation. Because remember, what we're doing with a sample is we're trying to describe the entire population. We're trying to have a representative sample. So the mean and standard deviation that we get, we're going to assume that those estimate the overall population mean and the overall population standard deviation. So don't worry about the distinction. The key is just, are you dealing with a sample or are you dealing with a population? If it's a sample, divide by n minus 1. If it's a population, divide by n. And I also want to point out that if you were to square standard deviation, you would get what's called the variance. So you could think about this as sigma squared and s squared. If you squared these, then that's what you would get. Oh, and I made there's a little typo here. This is actually the square root. Okay, so yeah. So that's what we want to point out. It's actually the square root of the average. The square root of the average of the square deviations from the mean. So we're going to unpack this in a moment. Again, the variance is just going to be the square of sigma. So that will actually be what I had when I was missing the square root sign. So if you square a square root, cancels it out. And s squared will be the sum of x minus the sample means squared divided by n minus 1. Variance is not something that we often use to talk about, but variance is an important thing in statistics. So if you hear about that, it's just the square of the standard deviation. Okay, let's unpack what is actually going on here. So we said that when we look at values, like if we looked at the 3 house prices in one of those cities, then the average house price was $350, and in city 1 we had house prices of $300 and $400. So in this case, this is a sample. So the sample mean is 300 plus 350 plus 400 divided by 3, which comes out to 350. Oh, and we're assuming this is in thousands of dollars. So 350,000 per home. So if all the homes were worth exactly the same amount, they would be worth 350,000, right? We'd kind of borrow 50,000 from this $400,000 house, give it to the $300,000 house. They would then all be equal at 350 if we redistributed the wealth. Okay, now we want to know how spread out they are. Well, the formula says look at the distance inside of the parentheses here. Look at the distance between each value and the mean. So the x minus x bar for 350 minus the mean, well, that's equal to 0, right? So 350 is 0 units away from the mean because it happens to be that one of our values is the mean. Now, if we do 300 minus 350, we get negative 50. Okay, negative 50 because it's $50,000 below the average house price. 400, we see that that's $50 above the average house price, and that's what we would get if we took x minus the mean. That's why it's important to subtract them in this order, because these are what we call the deviations. So these are the deviations from the mean. So this is how spread out the values are as a distance from the mean itself, right? This one was negative 50, this one was positive 50. This value relative to itself is 0 because it happens to fall exactly at the mean. So why don't we just average the spread together? Why don't we just add these up and divide by 3? Well, if you notice, what ends up happening here is that if I add up just all of these deviations that I just calculated, well, that will be negative 50 plus 0 plus 50. Well, that cancels out and gives me 0, right? That's not good, because that means that we're going to describe this data as having 0 spread. But clearly, the data isn't 0 spread out. It has spread in either direction. So the problem with this is that anytime you compute a mean and then look at the deviations from the mean and add them up, they're always going to be equal to 0. So I'll just say always. So the problem is the sign, right? How the negative 50 and the positive 50 cancel each other out. So one way, of course, is just to ignore the sign. And we don't do that in statistics. We won't get into that here, but a much better way of doing it is to, when you square a value, you multiply it by itself, you always get a positive value. You always get a positive outcome. So that's what we do. We add up the squares of those deviations, And now we're going to average them out, right? So if it's for a sample, we'll divide by, in this case, 2. 3 minus 1 is 2. If it were a population, we would divide by 3. And that gives us an average. But if you notice what's inside of here, we squared the values. So that's the average squared deviation. All right, well, that's a problem because we don't want to know how spread out these squared deviations are. So what do? Well, you know what? If we take the square root of it, then we've kind of undone, in a way, the square that we did in the first place. And so we're back to describing the average amount of spread. So the standard deviation can be interpreted roughly as the average amount by which values deviate from their mean. So example from the city homes. Let's take a look at this very first one. And here's an easy way to write these all out. First of all is just to list the values. We don't often do this by hand. We're just going to do it here so we can kind of understand where these numbers come from. So we have a sample. So down here, what I like to do is actually state my x bar, my mean, which I know is 350. Next, what I'll do is I'll list a column for my x minus x bars. So 300 minus 350 is negative 50, 0, and positive 50. And now in this next column, let me square them first, because we're going to add up those squares. Negative 50 squared is 2500. 0 squared is 0. 50 squared is 2500. And now add these up. Okay, so this is our numerator. So add these up and we get 2500 plus 0 plus 2500, which comes out to 5,000. Okay, now what we need to do is divide it by n minus 1 and take the square root. So s is going to equal the square root of that 5,000 divided by the number of values minus 1. Again, because we're dealing with a sample of homes. So if I take 5,000 divided by 2, I get 2,500. And if I take the square root of that, I get 50. 5,000 divided by 2, square root of 2,500 is 50. So we get a standard deviation of $50,000. Right? We squared dollars. We got dollars squared for a little while, but then we took the square root of dollars squared and we ended up with dollars. So how do we interpret this? Well, we'll say the following. City 1 has an average house price of $50,000. Also, house prices vary on average by $50,000 from the mean. Now, in this particular example, it just so happened that every house price was within $50,000 of the mean, and that's because we only had 3 values. So that's a way to describe it. That's how much they vary from the mean on average, right? It's not a true average, so because remember we divided by n minus 1 and then we took the square root of that whole thing, so it's not like really an average, but it's the easiest way to think about it. Now I want to show you how to do this in something like Desmos. In Desmos you can do this by pulling up this little keyboard here. You go to Functions, and under Statistics you have, first of all, mean. Okay, there's only one mean because it's always going to be the sum of the values divided by the number of values. If I do mean, do 300, 350, and 400, there's my average house price. And now if I do the standard deviation, I just have to be careful whether I'm talking about the population or not population. So STDevP is for population. That'll divide by n. STDev will divide by n minus 1. So if I do 300, 350, 400, I get exactly 50. But if I did STDevP, you get 40.83 or 40.82. So just keep that in mind. You can actually just type out stdev. That's why I'm just able to add that p afterwards. Now for city 2, rather than computing these by hand, let's go ahead and do the mean of 340, 350, and 360. And again, same average house price. Let me copy these. And now again, because this is a sample, I'll just do stdev. And now you see that my standard deviation is 10, right? The fact that that number is smaller means that on average, house prices vary by $10,000 away from the mean. Now, this worked out perfectly, right? 10 is kind of what you expected, and 50 is kind of what you did expect. But if you added another value in here, if there were another home price like 375, 375, so our mean changes. But also notice that our standard deviation is not a neat number anymore. So the reason that it was 50 and 10, it's not like you could just look at the values and automatically always deduce that. It's just because of the data set that I picked, it worked out to be nice. If I added like 350 in here again, now my standard deviation is actually smaller because notice that I have two prices right at the mean. Sorry, those aren't at the mean. My mean has changed. Oh, no, it is still 350, excuse me. Two house prices at the mean, so my standard deviation is now smaller because now I have more values and more of them are clustered near the average. And so, once again, just to wrap up, standard deviation is just a way that we could summarize the spread in our data and come up with good estimates, good summaries of our data that allow us to be able to compare across, for example, different cities.